Today we're going to shift gears a little bit and start studying heavenly motion. What this really means for us is that we're going to study the motion of planets, the motion of spacecraft, the motion of asteroids or meteors, or the motion of anything moving through space. Now we're going to relate this to circular motion, but not quite yet. It's part of the circular motion unit because it does ultimately tie together. But as I say, for a day or so, it's going to be a bit of a shift in gears before we return to that circular motion aspect of it. We're going to look at, for just a few minutes, a little bit of history, which we don't do very often in Physics 20, but we got to lead you to kind of the current understanding of heavenly motion. And we're going to do that by going through some of the previous understandings of heavenly motion. Let's go way, way, way back a couple thousand years, more than a couple thousand years. Aristotle in the 4th century BC, so almost 2,500 years ago, and then Ptolemy in the 2nd century AD. These guys both suggested that the Earth is the center of the universe. We call this the geocentric model, or the geocentric theory of the universe. The Earth is the center of the universe, and everything else, including the sun, revolves around that. Now, we don't currently believe that. Okay, we currently have a different understanding of how the universe works. But why? Why do we have a different understanding of how the universe works? Why don't we believe the sun is revolving around the Earth and all the other planets are revolving around the Earth? If you take a step back from that for a second and think about it, it makes complete sense on an everyday level that the sun is revolving around the Earth. We get up in the morning, we come to school, the sun is rising in the east. We look up in the sky a little bit later, oh, there it is in the southeast. Oh, a little bit later, there it is in the south. There it is in the southwest. There it is in the west, come time for sundown. The sun is going around the Earth. If we just looked at that and we didn't know any better, then we would probably assume the same thing as Aristotle and Ptolemy did. And that is that the sun is revolving around the Earth. We know different now. But the reason that we know different is because somebody told us different, not because we figured it out ourselves. You and I look up in the sky and we know that the sun doesn't revolve around the Earth, rather the Earth revolves around the sun. But only because somebody told us, not because we observed that ourselves. So these guys were completely wrong, but it wasn't such a far-fetched theory, given that nobody was around that knew different to tell them differently. So the geocentric, geo meaning Earth, Earth-centered theory, the Earth is the center of the universe, and everything else revolves around that, including the sun, including the planets, and including all the stars, and so on and so on and so on. Sun and all other stars, sorry. Not stars. Sun and all other stars, planets, and so on revolve around the Earth in circles. Let's fast forward now a couple thousand years to the 16th century AD. Copernicus, you guys have all heard of Copernicus, right? You might not know what he said or you don't know anything about him, but you've all heard of Copernicus at some point. He put forth what we call the heliocentric theory. Helio means sun, the sun-centered theory. All the planets, including the Earth, revolve around the sun. And this is more or less the current model of the universe, the heliocentric model. Planets, Earth, Mars, Jupiter, they all revolve around the sun. Let's fast forward another half a century or so, 40, 50 years, to a guy named Tycho Brahe. Got a little story to tell you about him in a second, but before I do that, let me tell you what he did. Tycho Brahe made observations of the planets with his assistant, Kepler. Kepler is the guy who's a lot more well-known than Tycho Brahe because Kepler did something with those observations. But those observations are still important. He looked up in the skies, and he made measurements of angles, and he made measurements of times, and he looked at where this planet is at this time of day, and where it is at this time of year, and so on and so on and so on. He collected a whole bunch of data that later on ended up being used by his assistant, Johann Kepler, in order to formulate some laws of how the planets move. We'll talk about those in just a second. There's a great little story about Tycho Brahe. He's kind of an odd guy. Well, really an odd guy. A couple little stories about him, actually. Him and a guy he's chatting with one day, getting this disagreement about math. So what do? Well, like true math people, they fight it out. But they fight it out with swords. What happened to Tycho Brahe when he fought it out with a sword? Literally over a silly math problem, got his nose cut off. So then he got a replacement nose that was made out of metal. So he's walking around with this metal nose, this shiny metal nose. That's odd enough. But wait till you hear this one. Tycho Brahe's at a dinner party one time. By the way, don't ever do this. Okay, if you ever find yourself in this situation, you should not do what Tycho Brahe did. So Tycho Brahe's at a dinner party. It's the late 16th century. Okay, maybe it's cold. I don't know. He has to go to the bathroom. Maybe he doesn't want to go to the outhouse because it's cold outside. I don't know. As the story goes, he didn't want to be rude. He's got to pee really, really, really bad. But he doesn't want to be rude, get up away from the table and go outside and go pee. So he stays there, and he stays there, and he stays there, and he has to pee more and more and more. Well, eventually, his bladder bursts. 12 days later, he dies. He died because he didn't go to the bathroom when he had to go to the bathroom. Okay, that's why when you guys ask to go to the bathroom, I always let you go, because I wouldn't want you guys to die because you had a burst bladder. Okay, that's not very common for that to happen. But it's happened. Okay? So Tycho Brahe will, for us, okay, whenever we review tomorrow and the next day on the same material, Tycho Brahe will be known from now on as Tycho Brahe, the P guy. Okay, so when I talk about Tycho Brahe, the P guy, you know who I'm talking about. He's the guy that made naked eye observations of the planets with his assistant. He's the guy that's in a dinner party and was too embarrassed to leave the dinner party and go pee, so he ended up dying 12 days later as a result of it. Tycho Brahe and his assistant made these observations. His assistant, Johann Kepler, also obviously in the late 1500s because he worked with Tycho Brahe, he took that data and he described the motion of the planets. Not they all revolve around the sun, because Copernicus already said that, but rather how they revolve around the sun, how they move around the sun. Specifically, what does the path look like as they go around the sun? So what exactly did Kepler's laws look like, these laws that he developed as a result of his and Tycho Brahe's data? Well, the first one is called the law of elliptical orbits. The law of elliptical orbits says this: the Earth and all other planets, for that matter, revolve around the sun in an elliptical path. Now, the picture that you see up on the board there shows two suns. There aren't two suns. There's only one. The Earth does revolve around one of those suns in an elliptical path, but not nearly as pronounced as that is. That's exaggerated big time. It's much closer to a circle than that's drawn. Why do we have two suns drawn there? Well, because the rest of the law of elliptical orbit says not only does the Earth revolve around the sun in an elliptical orbit, but that the sun is at one of the focal points of that ellipse. Okay, an ellipse has two focal points, right here and right here. The Earth is going to revolve around the sun, and the sun has got to be at one of those focal points. Now, the question that I always get from this is this. You've got your ellipse, and then the sun decides to be right there or right there, one of those two positions, okay, position 1 or position 2. No, the sun is where it is. The Earth, for lack of a better term, decides where to go based on where the sun is. So what you can say here is this. If the sun is right here, then the Earth will revolve around the sun in an elliptical path either like this, so that the sun is at the first focal point of the ellipse, or the Earth will revolve around the sun like this, where the sun is at the second focal point. The sun doesn't switch focal points. The sun doesn't change positions. The Earth decides, or whatever planet we're talking about, decides where it's going to go around the sun based on where the sun is. But the sun has to be at one of the focal points of the ellipse. Does that make sense? So we're drawing in two positions there. It's not really in two positions. It's at one of the two positions. Okay, it decides where it's going to be, and then the Earth revolves around it such that it will make sure that the sun is at one of the focal points. Let's write something down in words here. Let's say the Earth, and all other planets for that matter, planets revolve around the sun in an elliptical path with the sun at one of the focal points. Remember, it's not nearly as pronounced as I have the ellipse drawn here as well. It's much, much closer to a circle. The only reason that I draw it so pronounced there is so that you guys can remember that it's an ellipse. If I drew it the shape that it actually was, it would look too much like a circle, and you would automatically assume that when you see the picture that it's going to be a circular path. Okay, it's an elliptical path. It's just not quite as elliptical as this is. Yep. Yes. Yep. No, absolutely. It's absolutely possible to get big ellipses. It's just that when we look at the Earth and Mars going around the sun, it's not that pronounced. Second law, this one's a little bit trickier. This one's the law of equal areas. Now, before you copy this down, just pay attention. I'll give you a chance to copy it down in a second here. The law of equal areas, I'm going to give it to you in words, but the words aren't going to make a whole lot of sense. The diagram, once I complete it, is going to make a lot more sense, I think, I hope. The law of elliptical areas says this: a line joining a planet to the sun sweeps out equal areas in equal time intervals. A line joining a planet to the sun sweeps out equal areas in equal time intervals. Does that make sense to anybody? Probably not. Okay, it probably wouldn't make sense to me if I was in grade 11 and I heard those words for the first time. So let's take a look at the picture. Here's the sun right in the middle. We'll color it yellow. Here's a planet right here. Maybe it's the Earth. Okay, well, let's make it the Earth. The Earth is in a certain position as it revolves around the sun. Now let's draw a line that joins the Earth to the sun. It's an imaginary line that joins the Earth and the sun. Let's pretend it's a string, but obviously it's not really anything physical that's there. It's just this imaginary line. Now let's fast forward a month, or 2 months, or 3 minutes, or 10 minutes, or 6 months, or 7 months, or 6 days and 7 days. It doesn't matter. Let's fast forward a certain amount of time that we call T1. So after a certain period of time, T1, the Earth is no longer right here in position 1. It's now in position 2. So far, so good? Nothing crazy about this right now. The Earth changes position around the sun. I don't think that's groundbreaking. It's not rocket science, right? Well, kind of it is rocket science, but it's not hard rocket science, right? You got the Earth in one position, you got the Earth in another position after a certain amount of time that we call T1, that could be whatever amount of time. Let's fast forward a lot further in time now, maybe 6 months later. Doesn't really matter. The Earth is now at position 3. Let's fast forward a little bit more in time. Okay, T2. The Earth is at position 4. Here's the thing with Kepler's law of equal areas. If T1 equals T2, in other words, if we fast forwarded 3 weeks here, then we fast forwarded 3 weeks here. If we fast forwarded 6 days here, then we fast forwarded 6 days here. So in other words, if T1 equals T2, regardless of what that time is, if T1 equals T2, then the area swept out here, this area that's inside here, that's swept out by that line, that we call A1, that will be equal to the area swept out right here, that we call A2. So if this time is the same as this time, then this area is the same as this area. Does that make some sense? Does it make a little bit more sense than the words that I gave you when I first gave it to you? A line joining the Earth, or any other planet for that matter, a line joining the Earth to the sun sweeps out equal areas in equal time intervals. Now that has some pretty big implications including one that I'm going to tell you about. If T1 equals T2, this time equals this time, clearly when it went from position 1 to position 2, it went further in that amount of time. It traveled further, right? T2 is the same amount of time as T1, but didn't travel as far. What does it tell us about the speed of the Earth or whatever other planet that we're talking about? If the time is the same, but the distance is different, what does it tell us about the speed? Yeah, the speed of the planet changes. In fact, the speed of the Earth, or whatever planet that we're talking about here, Mars or Jupiter or the Earth or whatever, the speed of the Earth, when it's closer to the sun, is greater. Make sense? A line joining the Earth to the sun sweeps out equal areas in equal time intervals. So in other words, if T1 equals T2, then A1 must equal A2. That's the way that I'm going to write down this law. Even though it's not in words, it's more of a if-then statement. I think it still makes a little bit more sense to us than the original wording that I gave you. We got one more law now, kind of like Newton. Newton had 3 laws. Kepler has 3 laws. Kepler's 3rd law, called the law of periods. Now, this one can be really confusing if you don't listen real carefully, so pay attention. You can write this later on, okay? Don't write this down yet, okay? Kind of summarize it after I've got everything written down. What does T stand for? T is time, but specifically what time? The period. It's the period of revolution, the time that it takes for one revolution. So if we take the square of the period of revolution of a planet going around the sun, we square that value. For the Earth, that would be 365 days-ish, right? Not exactly, but pretty close to 365 days. If we square that period, then that's going to be proportional to or related to the cube of the distance that separates the Earth and the sun. And now that changes. So we're talking about an average distance here that separates the Earth and the sun. You can see that at one point in the year, the Earth is closer to the sun than it is at another point in the year. But the average distance, if we cube that, it's going to be related to, or it's going to be proportional to t squared. Now, what does that really mean? Does that really mean? Well, it means that t squared is equal to a number, a constant, times r cubed. What does that mean? What kind of implication does that mean? It means that t squared over r cubed is equal to a k, a constant k that we call Kepler's constant. Each thing that is revolved around has a certain value of Kepler's constant. The Earth has a value of Kepler's constant. When we're talking about the moon revolving around the Earth, Kepler's constant for the Earth is a certain value. When we're talking about the space station orbiting around the Earth, then Kepler's constant for the Earth is a certain value. When we're talking about anything revolving around the Earth, then Kepler's constant for the Earth is the same value. Now, we're talking about the sun. Well, Kepler's constant for the sun is a certain value. It's different than it was for the Earth, but it's a constant value for the sun. The Earth revolves around the sun, K is a certain value for the sun. Mars revolves around the sun, K is a certain value for the sun. The beauty of that discovery is that we can take data about the Earth revolving around the sun, the square of the time that it takes the Earth to revolve around the sun, the cube of the distance that the Earth is from the sun, and get a certain value for the sun. Then we can get from that data about any other planet. Because Kepler's constant for the sun, the object that's being revolved around, remains the same. Does that make sense? So let's say we've got the time that it takes the Earth to revolve around the sun. We've got the radius, the distance between the Earth and the sun. That will get us Kepler's constant for the sun. Now we can say, all right, look, I know what the radius or the distance of Mars to the sun is. Well, I also know what Kepler's constant for the sun is because I figured it out using data for the Earth. Now we can figure out the time that it takes Mars to go around the sun. So from data from the Earth and the sun, we can determine more data about Mars or any other planet. That make sense, guys? So the law says the square of the period of revolution of a planet around the sun is proportional to the cube of the average distance that separates the planet and the sun. But that doesn't make any sense to us, or at least it doesn't tell us what it really means. This is what really tells us what it means. T squared over r cubed is equal to a k. And that k is the same every time for whatever object is being revolved around. Now, you look at some other star somewhere out there in the universe, well, k is going to be a different value. You look at some planet like Mars, k is going to be a different value. K always is relative to what's being revolved around. Mars is revolved around by a moon, I'm not sure how many moons. Earth is revolved around by one moon. Kepler's constant for the Earth, okay, counts when something is revolving around the Earth. If you're talking about the Earth revolving around the sun, you'd be talking about Kepler's constant for the sun, which would be a different value than that for the Earth, but the same value no matter what is revolving around the sun. Okay? All right, so you can write down something right now that kind of ties that together. If you want me to put something in words, I can. But honestly, I think the explanation that I gave for this makes a little bit more sense than the actual law that says the square of the period is proportional to the cube of the distance that separates them. So this tells us how the Earth revolves around the sun and all planets revolve around the sun. It doesn't tell us why. Okay, to explain why, we need another guy. Okay, we had Aristotle, we had Ptolemy, we had Copernicus, we had Tycho Brahe, we have Johann Kepler. These are all important guys. These are all important people in the development of our current understanding of how and why the Earth and all other planets revolve around the sun. But it takes one more guy to determine exactly why it happens. That guy was Newton. We've talked about Newton's laws. Now we're going to talk about another law of Newton's. It's not the first law, the second law, the third law, or even the fourth law. It's another law altogether that's kind of independent of those ones. Here's what I want you to do. I want you to pick a partner. Okay, everybody has to have a partner. Everybody got a partner? I want you to look at that partner in the eyes. Straight in the eyes. Now, don't giggle here because I want to keep this serious, okay? Look at your partner in the eyes. Now, if you happen to have to share a partner with somebody, that's okay. Just kind of try to look them in the eyes as if you're giving them a really, really important message here, because this is important. Everybody look at somebody in the eyes? Don't giggle. It's not funny. Now repeat after me. You're not allowed to laugh here, remember. I am attracted to you. All of you guys, as much as you're giggling about that, and I told you not to giggle about it, all of you guys are attracted to each other. All of you guys are attracted to the desk that you're sitting on. All of you guys are attracted to the wall and the pen that's in front of you. All of you guys are attracted to everything else that has mass because you have mass. Newton said, as the story goes, Newton's sitting under a tree, an apple falls on him, and all of a sudden he has this epiphany that the apple falls toward the earth because it has mass and the earth has mass and things with mass attract each other. That's gravity. Okay, that's the discovery of gravity. He extended that to say, well, look, if the earth and the apple are attracted to each other because of gravity, then the earth and the sun will be attracted to each other because of gravity. Therefore, the centripetal force that keeps the earth in orbit around the sun is provided by gravity. That same force that acts between you and your partner that's sitting behind you or sitting next to you. The same force that acts between you and the earth. The same force that acts between any planet and the sun. We call it Newton's law of universal gravitation. And it's about 100 years-ish after this whole thing about Kepler's laws of equal areas and Kepler's law of elliptical orbits and Kepler's law of periods. Finally, after 100 years, somebody comes along and says, this is why it happens. Not just this is how it happens, but this is why it happens. And Newton said that any two objects with mass have a force of gravity on each other, including you and your neighbor. Now, the value of that force is related to the values of the masses, but inverse related to the distance that separates them. So in other words, the bigger the two masses, the bigger the force of gravity. The bigger the distance that separates the masses, the smaller the force of gravity. When an apple falls to the ground, this is why. When Mars revolves around the Earth, this is why. Something has to provide that force, and it's gravity. Now, this seems to explain everything, right? We know everything now. It's 1687. We know everything. We know how the Earth revolves around the sun. We know why it revolves around the sun. It's all good. Newton had a little secret, though. He knew that two objects of mass would attract each other, including him and the apple, including him and somebody standing on the other side of the room. But he couldn't explain at a deeper level why two objects with mass attracted each other. Think about that. Okay, most of you probably just, or all of you, just accepted that when I said, oh, two objects with mass have a force of gravity on each other. All right, that explains everything. No, it doesn't. Why do two objects with mass attract each other? It wasn't until the 20th century that we established that. And I'm going to briefly tell you about it, but you're not going to write it down because that's not really a part of Physics 20. Anybody know who that was in the 20th century, by the way, that explained why two objects with mass attract each other? It's a pretty big name, named Einstein, right? Einstein came up with the theory of relativity. I'm going to give you an analogy to help you to understand the theory of relativity and why two objects with mass have a force of gravity that act between each other. Let's say we've got four people here. 1, 2, 3, 4. You guys are all standing in a square, and you've got a blanket that you're all holding a corner of. So corner 1, corner 2, corner 3, corner 4. And you're holding that blanket tight and level, perfectly level, and it's nice and tight so that it's flat. That blanket will represent for us the fabric of space-time. Einstein said that you don't have space. You don't have X, Y, and Z. You have space-time. Time is a fourth dimension. Okay? Now, that fabric will represent, or that blanket will represent the fabric of space and time. Right now, it's flat. It's all good. It is not in the universe. It is the universe, this blanket. Now, what happens when I put a little marble at the corner of that blanket? Marble just stays there, right? Because it's all flat. What happens when I put a big rock in the middle of that blanket, and then I put the marble at the corner? What happens to the marble now? It goes down toward the big rock, right? Einstein said that things with mass, like the sun, for instance, dent the fabric of space-time. They bend the fabric of space-time. Therefore, things are attracted to that heavy thing that dented the fabric of space-time because of the curvature of space-time. Now, this little marble is going to roll down the curvature of space-time toward the big rock. Just the same as if I was traveling out in space toward the sun, I would be pulled in towards the sun. The fabric of space-time would basically provide a slide for me. I'd be sliding down this fabric of space-time toward the object that caused the dent. Does that make some sense? So we've gone from, hey, the Earth is the center of the universe, all the way up to, no, the sun is the center of the solar system. Everything revolves around it in the elliptical path. This is how it does it. This is why it does it, because of gravity, and this is why gravity acts. Tomorrow we'll get into some math. Okay, that's it for today, though.